off last time with the first isomorphism theorem for rings, so let me just remind you, right? So if you have a homomorphism, then you know that R mod the kernel of phi is isomorphic to the image of phi. And of course, this looks, I should just say homomorphism here. This looks exactly like the statement that we had in group theory, but of course the difference is now I'm using a capital R here, so that means that we're working with rings. This is a ring homomorphism, and the statement looks exactly the same. The proof is essentially the same. Or in fact, we really didn't have to do a whole lot extra other than verify the multiplicative aspects of this. So now what I want to do, some applications of the first isomorphism theorem. So the first example, what I want to do, so we're going to show that R bracket x mod the ideal generated by x squared plus 1 is isomorphic to the field of complex numbers. And we looked at this example where we kind of played around with the cosets here, and we got a hint. All right, I kind of hinted at the fact that the operations actually behave just like the operations that we do in when we're multiplying and adding complex numbers. Now that we have the first isomorphism theorem, we can actually prove this directly. So, well, let me show you, let me just remind you how we're going to set this up. I said at one point that the evaluation mapping was an important mapping, and we haven't really done much with it yet, but now we're going to. So remember, if you have this situation, you don't need to write this down because you already have this. So if you have some field that's a subfield of a larger field, and an element of the larger field, then there was the evaluation mapping phi sub alpha that goes from f bracket alpha into E, and what do? You do phi sub alpha of a polynomial is just the polynomial evaluated at alpha, right? So you don't need to write this down, but now we're going to make use of this in one particular case, and so consider the evaluation mapping phi sub I, where I is, right, the square root of minus 1 living in complex numbers, from R bracket x to C. We know it's a homomorphism, so I don't need to do the work there in verifying that it's a homomorphism. According to the first isomorphism, then, R bracket x mod the kernel is isomorphic to the image. So let's first identify the image. Given, let's say, a plus bi in C, note that phi sub I of the polynomial a plus bx is equal to a plus bi. And so no matter what, if I choose a complex number, I can find a polynomial whose output is that complex number. So we can say, and so phi sub I is surjective. All right, so the image of phi sub I is all of the complex numbers. So next thing we need to do is identify the kernel. Right, so now what I need to do, I want to show that the kernel of phi sub I is equal to this ideal. So we show that the kernel of phi sub I is equal to the ideal generated by x squared plus 1. And if we can do that, then we're done. First isomorphism theorem does the work for us. So so let's pick, we're going to go, I'll pick something on the left-hand side and show it contains or lives in the right-hand side. So let's pick some polynomial, say f of x, in the kernel of phi sub I. Now, I'm going to run the division algorithm on that. So by the division algorithm, f of x is equal to, let's say, what's it equal to? It's equal to x squared plus 1 times q of x plus r of x, where the degree of r of x is going to be less than 2, right? So strictly less than 2. Okay, so what does that mean? That means that we can write r of x as, so we can write r of x equal to a plus bx, where it's possible that one or both of a and b are equal to 0. That's fine. So then, then what? We know that when we plug alpha into our I into our polynomial, we get 0, right? So that's going to be 0 equals phi sub I of f of x, which is phi sub I of this expression here, so that's x squared plus 1 times q of x plus r of x. Good thing we have a homomorphism here, so this is phi sub I of x squared plus 1, phi sub I of q of x plus phi sub I of r of x. I'm going to continue this equality, but I'm going to move it up to here where I've got a little bit more room. Notice what happens when we do phi sub I of x squared plus 1, that's 0. And so it's going to be phi sub I of r of x, which is equal to a plus bi. So what we have then is that 0 equals a plus bi, right, which tells us that both a and b equal to 0. So it follows that a equals b equals 0, which means then that f of x is just this, right? This implies that f of x is in the ideal generated by x squared plus 1, right? Polynomials in this ideal are of the form x squared plus 1 times some other polynomial. All right, so that gives us containment in one direction, so we can say thus, sorry for the cramped quarters here, so thus f of x, let's say like this, thus the kernel of phi sub I is contained in the ideal generated by x squared plus 1. Now, in the reverse direction, so let's pick somebody. So let's say pick g of x in ideal generated by x squared plus 1. Then, let's see, g of x, well, it's going to look like x squared plus 1 times h of x for some h of x in r bracket x. And now, phi sub I of g of x, I'm going to plug g of x into this, and that's going to give me phi sub I, let me just do it all at once, x squared plus 1 phi sub I of h of x. But when you plug I into x squared plus 1, you get 0, so this is equal to 0. Thus, the ideal generated by x squared plus 1 is contained in the kernel of phi sub I. So now we have equality. So now, okay, so what does that mean? We have ideal generated by x squared plus 1 is equal to the kernel of phi sub I by the first isomorphism theorem, r bracket x mod kernel of phi sub I is isomorphic to the image. Let's write it out like this. And so, r bracket x mod ideal generated by x squared plus 1 isomorphic to C. That was fun, right? I mean, there's no other way to say it. This is also amazing, right? What we did, we took a quotient by a polynomial. I mean, look at this. I mean, the x squared plus 1, right? What we're trying to do with this, we want this to be the kernel, right? We want to take this. So what we're doing is telling all polynomials of this form, or with this as a factor, to be 0 in the quotient, right? We're killing that part off. Right? Well, x squared plus 1 equals 0 should make you think, oh, x squared equals -1. And so that's kind of where the connection comes from. But in a way, when you first see this especially, this is amazing. Right? Very fun. Let's look at a couple more examples. Well, I guess I'm going to do one more example and then a theorem. I feel like I missed something. Oh, no. Here's another kind of interesting fact. We'll see this. This will show up again later on. So let's consider evaluation. So it'll be phi sub 0. I'm going to go from z bracket x to z. Then phi sub 0 should be clear that phi sub 0 is onto. But check this if it's not completely obvious. And let's see, who's the kernel? Well, so we're plugging 0. If you're going to plug 0 in and get the identity, or get 0, that means it's got to have a factor of x. And so the kernel of phi sub 0 is the ideal generated by x. Check the details on this. Therefore, what do we have then? Z bracket x mod the kernel is isomorphic to the image, like that. We're going to need this fact a little later on. And so I want to finish off this chapter with a theorem. So this is 26.7. And I want to give this a name. So this is properties of homomorphisms. Part 2. Right? We already had a theorem that gave us some of the properties of homomorphisms, but at that time we did not know what an ideal was, right? And so this theorem here is going to tell us how homomorphisms behave with respect to ideals. So so let's let phi from R to S be a homomorphism. Two parts of this. So if I is an ideal of R, then the image phi of I is an ideal of S. Oh, no, sorry, not of S, of the image of phi of R. And then part B, if, right, remember how subrings go to subrings of, right, the image. Same thing here, if, well, not same thing, if J is an ideal of S, then the inverse image of J is an ideal of R. I just want to hold up for one thing. I feel like, let me just hold on for 1 second. So, sorry, I know this is weird, but I want to look in the book real quick because I feel like this was a homework problem and I just want to see how they worded it. I feel like I saw it last night and they worded it kind of weird. Well, whatever, I don't know. Oh, yes, sorry. Yes, they worded it a little bit weird, and that's fine. In the end, it says the same thing that this one does. So what I want to do, I'm going to prove one of the parts and then leave the other one for you. So let's look at part A. Okay, so I need to apply the ideal test. So let's let... Oh, okay, first of all, it's non-empty. So since 0 is in I, phi of 0 is in phi of I. And so phi of I is not empty. Okay, now we need to show that it's closed under subtraction, which we already know this because an ideal is a subring, but I'll just go through the steps. So now let's pick A and B in phi of R. Then A equals phi of X and B equals phi of Y for some X and Y in capital I. So now A minus B is equal to phi of X minus phi of Y, which is phi of X minus Y. Now, since I is an ideal, it's a subring, which means it's closed under subtraction. So we can say since X minus Y is an element of I, we see that A minus B is an element of phi. Okay, now we need to prove that it's closed under external multiplication. And remember, we're showing that it's an ideal of phi of R. So now, let let's say S be an element of phi of R. So then S, phi of capital R. S is equal to phi of Z for some Z in capital R. So it follows that, so now I need to do R times S, so RS, not R, yeah, wait, what? Not RS. I need to do, I want to show that it's closed under external multiplication, so I would do S times A, sorry. S times A is equal to, let's see, S is phi of Z, A is phi of X, which is equal to phi of ZX. And let's see now, Z came from R, A came from X came from I. So now, or since Z is in R, X is in I, and I is an ideal, we have that ZX is an element of I. Therefore, what? S times A is an element of phi of I. A similar argument shows that A times S, so similarly, A times S is an element of phi of I. So now by the ideal test, phi of I is an ideal of capital R. Part B we'll just leave as an exercise. All right, so that completes the proof. And that's as far as I want to go. We're going to start a new chapter next time. So we'll stop here and see you then.